it's making sure that everything is in line and is in view. So let me just start from the top. Let's get this in play, okay? And again here we're looking at settings, and I noticed that I had a couple of shots in the last video out of frame. Okay, right, session 1, apologies, session 9, Transformers 1. Session 9, Transformers 1, okay? Aimed and objective of this session to understand what a transformer is, to be able to state how it works, to be able to do power calculations, okay? Okay, sorry, I just on my feet there. This is just all recap session, okay? So bear that in mind, okay? Let me just make sure I can get an interview. Okay. Transformers. The transformers come in many shapes and sizes, but basically operate the same way. Okay, 3-phase pole-mounted step-down transformers, laminated core transformers showing edge of laminations at top of unit. Okay, current transformers. Okay, potential transformers. Now, if you don't know what potential transformer is, look it up. Okay, if you want a bit more information on current transformers, look those up as well. But you'll find that the information is readily available. It's not a secret. Okay. Simple transformers. Now, when we have a change in magnetic field, an induced EMF is generated within the coil. This means when a second coil is brought close to the current carrying conductor, then an induced EMF is generated within that second coil. This is the basic principle of a transformer, okay? And always showing you here. Now, each core is sliced and laminated. That the idea here is to reduce eddy currents, thereby reducing the heating effect of the transformer, okay? And if you reduce the heat, the transformer will be more efficient, and it will last a lot longer. Okay. Simple transformers, again here, and showing you a again here you can see the right hand rule. The current in the primary winding shown here produces a magnetic field with the north-seeking pole going in a clockwise direction. This has been found using the right hand grip rule. The magnetic field is retained in materials such as iron or steel, as they are easy to magnetize. Okay. Lenz's law, and you would notice that we've just covered a bit on this already. All this is now doing is just recapping basically how that data has been applied in the transformer situation. The magnetic field is varying, so there must be an induced EMF in the secondary windings. This is found by Lenz's law. Lenz's law states that the EMF induced in a conductor or coil acts to circulate a current in a direction that opposes the change of magnetic flux that gives rise to the induced EMF. Whatever causes a change is to be opposed. Okay, so you apply for a voltage to the circuit, then Lenz's law says you will get an opposition to that applied voltage. And again here, again a bit more on Lenz's law. Okay, the primary has a current flowing in it, which has produced a magnetic circuit in the material. This is moving in a clockwise direction. The primary magnetic field is linked to the secondary winding, which has induced an EMF in that winding. The EMF in the secondary winding produces a constantly changing current, which produces a further magnetic field around the secondary. This magnetic field moves anticlockwise, opposing the initial field. Okay, and that is what Lenz's law is trying to indicate and say. Simple transformer with labeled current and fluxes. Here just your diagram showing you your current and the flux phi. Okay, supply voltage, primary winding, number of turns. Okay, this diagram shows the varying magnetic fields and in which direction they are moving. Okay. So I tried to garble it out before I had quite finished. Power. Power is defined as rate at which work is done. Energy is defined as work done or work. This is true for electrical power and energy. When a current flows in a resistive circuit, heat is given off, energy released. The rate at which the heat is given off is determined by the power of the circuit. The formula that describes the energy converted in an electrical circuit takes three forms. W equals ULT, W equals I square RT, W equals U squared times T over R. The three common equations used to determine power are P equals I times U, P equals I squared R, P equals U squared over R. Okay. Funny, I was looking for an example of this actually. I was looking for an example of this. I was hoping to give you the maximum, but maybe we don't need an example just yet. It'll come up a little bit later, but be sure that you write out the examples when they're given. Okay, put pen to paper, you cannot go wrong. Okay, thank you for your time. Have a good day. Bye bye.